Hello and welcome to our next lecture. Today we're talking about delta function in modeling system with shock-like inputs. First I want to get one thing out of the way. Despite its name, delta function is not a function. Delta function is a mathematical object that is used to model shock-like phenomenon. To get to the delta functions, let's consider a function that is a good approximation of a hammer-like action. I define the function that I call p t naught epsilon. That has the following. It is 0 all the way up to the time t naught, at which point it jumps up and it is non-zero for some period of time, and then it jumps back down to 0 after some period epsilon has passed. So the width of the interval on which this function is non-zero is exactly epsilon. And the value that it has is 1 over epsilon. We can think about it as a short burst of force for the time interval epsilon, and the magnitude of the force is 1 over epsilon. So if we make epsilon very small, then this will be like striking something with a hammer. Note that the area under the graph for this function is always 1, because the width of the impulse is epsilon and the height of the impulse is 1 over epsilon. So what happens if I take this function and I integrate another function together with it? Well, since this function is 0 almost everywhere, this integral is only going to be having a non-zero integrand from time t equal t naught to time t equal t naught plus epsilon. And f of t for this period of time will be multiplied by 1 over epsilon. If you remember mean value theorem for integrals, this is exactly an average value of f on the interval from t naught to t naught plus epsilon. And we know that the continuous functions achieve their average value at some point z that is inside the interval from t naught to t naught plus epsilon. Making epsilon smaller will make z go towards t naught. So if we take the limit and let epsilon converge to 0, and t naught plus epsilon will converge to t naught. And since z is stuck between them, z will converge to t naught as well. Then the limit, as epsilon goes to 0, of integral from 0 to infinity of f of t times p t naught epsilon is the same as the limit as epsilon goes to 0 of f of z, which converges to f of t naught because f is a continuous function. So we see in the limit, my function p has this interesting effect. It just evaluates the function at t naught. But this is very strange because the function p converges to the function which is always 0 except at t naught. And it seems like at t naught the function converges to the infinite value. And no classical function will have properties like that. So therefore, the limit of the function p is not a classical function. What it is, it's a mathematical object, which we call the delta function. And we denote it as delta of t, with delta being a Greek letter. And the delta function has this property that if we take any function and integrate against delta t minus t naught, shifted by t naught, then we get either f of t naught, if t naught is inside the interval from a to b, or it's going to be 0. If t naught is outside of the interval a to b. Notice that I didn't include the right-hand boundary. This is due to the fact how I defined the function delta as a limit. This is due to the way I defined the function delta. For some other definitions, the endpoints might be both excluded or both included. It doesn't really matter for us. As these distinctions don't make much difference for us. One thing I need to say is that f of t needs to be continuous at t naught. Because otherwise the limits above are not going to be defined. I want to add one important remark. What if I integrate my delta function just by itself? Then the result is going to be 1 if t is greater than t naught, or 0 so if I plot this function, this is going to be its plot. The function is going to be 0 until it reaches t naught, at which point it jumps to 1. And we know a function that does something like that. It's called a Heaviside function. Except that Heaviside function is defined to be 1 at t naught. But again, this doesn't make much of a difference for us, because the values of the function at a single point don't make any difference for integration. So in a sense, what we have is that the derivative of h of t minus t naught is the function delta of t minus t naught. Because as you can see, the integration I have up here is the antiderivative of the delta function. Well, this doesn't make much sense because we know that the discontinuous functions are not differentiable. And so this is in direct contradiction with what we learned before. And this is why I'm saying that the delta function is not a classical function. It's not differentiable in classical sense. Neither is h. H is not differentiable at t naught. However, when you start talking about theory of distributions, derivatives like that are quite well defined. For those of you who are interested in distributions, I recommend reading the books on partial differential equations, because theory of distributions plays an important role. For us, all we need is this definition of a delta function. So what is the Laplace transform of the delta function? By definition, it's going to be the integral from 0 to infinity of the delta function of t minus t naught times e to the minus st. And the delta function will just evaluate the exponential function at t equals t naught. So it's going to be e to the minus st naught. Again, only for t naught greater or equal than 0. In particular, the Laplace transform of just the delta function when t naught is exactly 0 is going to be just 1. And if you were wondering why all of our Laplace transforms look like fractional terms, this is the answer. Functions that don't have fractional terms as Laplace transforms are very bizarre functions. So for example, the function that will have a Laplace transform s must be the derivative of the delta function. And yes, within the theory of distributions, derivative of a delta function is a quite well-defined function. As I said, we're going to use the delta function to model shock-like phenomena. Within the theory of differential equations, we've never seen something that will have a derivative as a delta function. But within the theory of Laplace transforms, delta functions are not a problem. So if we compute Laplace transforms, we get that s squared times y of s minus s times 1 minus 0 plus 3 times s times y of s minus 1 plus 2 times y of s should be the Laplace transform of the delta function t minus 2, which is e minus 2s. Grouping the terms together, we see that y of s is multiplied by s squared plus 3s plus 2. And that should be equal s plus 3 plus e to the minus s. Therefore, the Laplace transform of the solution is s plus 3 over s squared plus 3s plus 2 plus e to the minus s over s squared plus 3s plus 2. Apologize, it's e to the minus 2s. I keep these two terms as separate fractions because later on the second fraction is going to give us an expression that's going to be shifted by 2 units. The next thing we need to do is to compute the partial fraction decomposition. For that we need to factor out the denominator. The partial fraction decomposition is quite easy to compute. However, let me just do it with Mathematica. So we need the partial fraction decomposition of s plus 2 times s plus 1. And I also need partial fraction decomposition of 1 over s plus 2 times s plus 1. So we have 2 over s plus 1 minus 1 over s plus 2 plus e to the minus 2s multiplied by 1 over s plus 1 minus 1 over s plus 2. Inverting this is quite easy. I get 2 e to the minus t minus e to the minus 2t plus I get two functions, e to the minus t shifted by 2 units minus e to the minus 2t shifted by 2 units. Let's look at the graph of this function. As you can see, this graph has an interesting event happening at 2. Let's look at where this thing can come from. If we looked at the original equation, then we can say that one of the terms, the y prime or y double prime or y itself, should have delta function in it. But with each successive derivative, the terms will get nastier and nastier, and delta is quite a nasty term itself. So it must be that the y double prime should have a delta function in it. And if y double prime has delta function in it, y prime should be the antiderivative of it, so it should have a step. And since y prime is discontinuous, y should have a corner. And that's exactly what we observe here. We see that the derivative is quite nice, but at 2 it ceases to exist. We have a corner for the function. That means the derivative experienced a jump, and then the derivative continues to exist for the rest of the t values. Let's look at the derivative of this term. So the Mathematica tells us that the derivative is going to have a Dirac delta function and a Heaviside function. So it's going to have a jump, and it's also going to have a delta function in it. But wait a second. If we look at this term at t equals 2, this is going to be e to the 0, so it's going to be 1. And this term at t equals 2 is also going to be e to the 0, so it's also going to be 1. So these two terms will zero each other out, and so the Dirac delta will disappear at t equals 2. And since Dirac delta is 0 everywhere else, I'm sure this will simplify into something that will not have Dirac delta in it. And just as I said, Dirac delta function disappears when we simplify this expression. Let's plot this expression and see what happens with our derivative. And just as I said, the derivative experiences a jump right there at 2. Up to 2 the derivative was negative, and then at 2 it jumped to be positive, and then went back to be negative again. This is exactly what we expected to see. Let's also look how delta function can be seen as the input for systems of linear equations. In this example we have a quite simple linear system. It's a 2 by 2 system, and the second component has a delta function applied to it at t equals 2. So again, let's apply Laplace transform and see what happens. S times the vector of the Laplace transforms minus the initial conditions should be the matrix multiplied by the Laplace transform of the vector y plus the Laplace transform of the forcing term, which is 0 for 0 and e to the minus 2s for the delta function. Hence we have the following. This matrix times y of s should be equal to 1 plus 0 e to the minus 2s. Solving for y of s gives us the inverse of this matrix, which I'm going to simplify into s plus 2 minus 1, 0, and s plus 1. So we need to invert this matrix and multiply by the vector 2 on the top and 1 plus e to the minus 2s on the bottom. Computing the inverse gives us 1 over the determinant of the matrix, which is s plus 2, s plus 1. And inside the matrix we'll switch the diagonal elements and negate the off-diagonal elements. Computing this, we get 2 over s plus 2 plus 1 plus e to the minus s divided by s plus 1 times s plus 2. And for the bottom we have 1 plus e to the minus s over s plus 1. The first component has almost all of its terms in partial fraction decomposition. For the second term, we need a partial fraction decomposition of 1 over s plus 1 times s plus 2. But we already know the partial fraction decomposition for it. Because it's the same fraction as in the previous example. This is 1 over s plus 1 minus 1 over s plus 2. Therefore, y of s can be written as, we get 2 over s plus 2 minus 1 over s plus 2. So it's just 1 over s plus 2 plus 1 over s plus 1 plus e to the minus s multiplied by 1 over s plus 1 minus 1 over s plus 2. For the bottom we have just two fractions, 1 over s plus 1 plus e to the minus s over s plus 1. Inverting this is quite easy. We get e to the minus 2t, we get e to the minus t, and we also get e to the minus t minus 2 minus e to the minus 2 t minus 2 shifted by 2 units. For the bottom terms we have e to the minus t plus e to the minus t shifted by 2 units. I apologize, again I skipped out the 2 in my exponential terms. So I get e to the minus t minus 2 times h of t minus 2. So if we look at what's going on with these terms, the second term has a step that's becoming active at t equals 2. For the first component, when t is equal to 2, I have h jumping to 1, but both of the functions I have here evaluate to 1, so this jump is reduced to 0. However, as time progresses, these two functions evolve differently, so what I'm expecting to see is an abrupt change of the behavior of the function at t equals 2. So let's go ahead and plot these two functions. I'm using curly braces to tell mathematically that I'm plotting two functions. So the first function was e to the minus 2t plus e to the minus t plus e to the minus t shifted by 2 units minus e to the minus 2t shifted by 2 units multiplied by Heaviside function of t minus 2. That's the first component. The second component is e to the minus t plus e to the minus t minus 2 times the Heaviside function of t minus 2. The purple curve is the plot of the first component, and as I said, it's going to have an abrupt change at t equals 2. The second component has a jump discontinuity at t equals 2, and that's expected since the derivative of the second component had a delta function in it. For the first component, its derivative had second component fed into it, and so the derivative of the first component should be the one with the jump discontinuity. And that's exactly what we see here. The first component evolves continuously, and it has a jump discontinuity in its derivative at t equals 2. The last thing I want to do today is to investigate what kind of a theoretical influence delta function has on systems. So consider a model of the mass spring dashpot system that was initially at rest, and at time equals 0 a delta function was applied to it. So it's like someone came to the system and hit it with a hammer. Doing the Laplace transforms will get us m times s squared times y of s minus s times 0 minus 0 plus gamma times s y of s minus 0 plus k times y of s. And that should be the Laplace transform of a delta function, which is 1. Solving for y of s, we'll get that y of s is 1 over ms squared plus gamma s plus k. And if you remember, this was exactly the system transfer function for this model. And therefore y of t is the inverse Laplace transform of the system transfer function in this case. This is quite interesting. We can physically see the effect of a system transfer function if we come to the system and hit it with a hammer. In the world of partial differential equations, these functions have a name they're called Green's function, because the function y of t that I have here can be used to figure out any response to the system to any other input. Remember that the system transfer functions multiply, but in the time domain what happens is the convolution. So if I compute the convolution of this y of t with any other signal, I will get the response of the system to that signal. So this property of generating all possible responses for this particular function is quite important. It is discussed in the context of differential equation as a Green's function. We have a similar effect on systems of linear equations. Suppose f of t has only one of its components to be delta function. What would be the effect of applying this to the system? If we use the Laplace transforms, Laplace transform of f of t is going to be 1, 0 in this case. Therefore, solving for y of s, we get it is the inverse of this matrix, which is what we call the system transfer function for the system of linear differential equations, multiplied by 1, 0. This multiplication will give us the first column of the system transfer function. Similarly, if we apply delta function to the second component, this will have an effect of extracting the second column of the system transfer function. I want to conclude with a couple of remarks. So first of all, as I said, the delta function is not a function. It's a mathematical object that's used to model the behavior of systems that being acted with. This is very useful in context of electrical circuits, as delta function can be used to model static discharge or other types of shocks. In mechanical systems, delta function acts as a model of a hammer-like action. In partial differential equations, delta function is used to model point sources of heat, for example, when you heat up a plate with a laser point. So the delta function is quite a useful mathematical tool. And despite its confusing name, it's not a function. Delta function is defined by its integration property. And if you want to be precise, delta function is its integration property. It's not a function, it's just a mathematical object that never works without the integration. And you might say, well, we used the delta function on initial value problems, and we used it as an input. Not really. When you solve in differential equations, you do an integration. Remember the variation of parameters formula. The solution to the differential equation is computed as an integral. And the same story goes for the systems. In order to get the solution, you integrate against the so-called fundamental matrix. Hence, the use of delta function in this context is quite appropriate. So I hope this is quite a good idea of what a delta function is. I appreciate you tuning in, and I'll see you in the next video.